Hey guys, today we are going to talk about metallic bonding. And like I said yesterday, metallic bonding is metals bonding with other metals. So let's review the properties really quickly. I know we've become very familiar with them. And we're not only familiar with them because we've talked about them in class. Okay, we interact with metals all around us in our everyday lives, from the metal spoon or fork that you eat with, to the wiring in your house. Okay, so these properties are familiar. We have that they conduct electricity. Okay, we know that. We've tested them ourselves in class. We know that they're shiny, most of them. They're malleable. Okay, they're able to form, they're able to take a different form without breaking. And they're ductile. That's one that we haven't really talked about in class. That just means that it can be drawn out into a thin wire. So that's why metals are used for wiring or piping in buildings. Okay, so the reason that metals have these actually specific properties is because of the way that their atoms are held together. So let's talk about that. Okay, so let's take magnesium for example. Think of the magnesium ribbon that we had when we were testing the conductivity, okay, that magnesium ribbon. When we have a piece of metal, in this case magnesium ribbon, you know that you have a whole bunch of magnesium atoms all grouped together. Okay, so here I have drawn a bunch of magnesium atoms all grouped together. So let's say that all of this is a piece of magnesium ribbon. Okay, so we call this structure, the atoms of metal, we call this a crystal lattice. Okay, what I mean by a crystal lattice is it's just a regular 3D arrangement of atoms. Okay, so kind of think of apples or oranges in the grocery store, how they're all nicely stacked up in that pyramid. Okay, so that's kind of how atoms are arranged in metals. Okay, so what's holding them together? When we're talking about neutral atoms, so let's say we're talking about neutral magnesium atoms here, there's nothing that seems like it would be attracting. We know that positive atoms attract negative atoms and vice versa, but if we're talking about neutral atoms, what's holding all of these magnesium atoms together? Okay? Well, if you look inside the magnesium atoms, there are positive and negative charges. We know that atoms have protons and electrons, okay, and neutrons, but those are neutral. So we're going to stick with the protons and electrons here. So we know that atoms have protons and electrons, positive and negative charges. That's what creates our glue. Okay, that's what creates the attraction that holds this piece of metal together. So consider magnesium's orbital filling diagram. There we go. There's nothing in the 3p. So the orbital filling diagram is 1s2, 2s2, 2p6, 3s2. Okay, that's magnesium. Look at the outermost shell here. Okay, look at this 3 shell, the third shell. Okay, there are only 2 electrons in it. There's not that many. Okay, remember I said that before. Metals don't really have that many outer electrons or valence electrons. Okay, and we know from the photoelectron spectroscopy graphs that the further an electron is away from the nucleus, the easier it is to move. Okay, so here we have 2 electrons that are decently far away from the nucleus compared to these other electrons. Okay, so every magnesium atom in this crystal lattice is going to lose these 2 electrons. Okay, so these electrons are not held very closely to the atom due to their spacing away from the nucleus. Okay, so this crystal lattice, every single one of these magnesium atoms, they are losing these outer 2 electrons. Okay, so that leaves behind a core. It's not really even a nucleus. So that leaves behind a core of a magnesium atom with a +2 charge. Okay, so you're taking away 2 electrons. That gives it a +2 charge. Okay, so if you look here, okay, I gave a +2 charge to all of these magnesium atoms. Okay, so these 2 electrons, these are leaving each of these magnesium atoms, and we are gaining a +2 charge on each of them. but where do these electrons go? Okay, so we have something called an electron C. All right, so pretend that this purple highlight here, that's just all the electrons. Okay, they're moving throughout all the atoms, all those lost electrons. So the definition of an electron C is valence electrons. Okay, so we are now going to refer to the outermost electrons as valence electrons. An electron C is valence electrons attracted to all the positive metal ions. Okay, so we kind of just have a smear of electrons all over the crystal lattice of magnesium here. Okay, so those electrons are shared by all of the magnesium atoms. This is called a non-directional bond. Okay, so electrons are being attracted by all of the positive magnesium atoms. They're not really sticking or bonding to one or the other. They're kind of just moving throughout that electron C. That's why it's called an electron C. Okay, so where's the positive negative attraction? Well, the electrons that are lost from the outer or valence shell of the magnesium, those are being attracted to the remaining positive magnesium ions. And remember, an ion is an atom with a charge. So all bonding always comes back to positive and negative attractions. All the bondings that we are going to talk about in this unit all come back to positive and negative attractions, okay? So the electrons, these two electrons right here that we're losing from the 3s subshell, okay? Those are all being shared, okay, from these now positive magnesium atoms, okay? So let's think back to the beginning of this video when we talked about the properties of metals. Okay, so this electron C actually leads to the properties that we see in metals. Okay, for example, we know that metals make good conductors of electricity. We saw this firsthand in lab. Okay, since these electrons are not attracted to any particular magnesium ion, okay, remember they're just moving throughout that electron C. They're not really bonding or sticking to one or the other. They're moving throughout all of them. It doesn't matter where they are. They can very readily move throughout your piece of magnesium. A flow of charged particles means it's conducting electricity. Okay, moving electrons. That means that you have a moving charge, electricity, conductivity. Okay, another one, metals are shiny. That's light interacting with those freely moving electrons. And the other ones we talked about, malleable and ductile, they can move atoms relative to one another because they are still a part of that electron C. Okay, so the metal has the ability to move the atoms, okay, without interrupting those attracting forces that are holding the metals together. Okay, so I know that was a lot and we'll talk about them in class and we'll do some more examples. Okay, but just to review, in a metal, the atoms are in a crystal lattice. Okay, so they're arranged in a crystal lattice. When you look at the electron configuration of whatever metal you're talking about, you'll notice in most metals, okay, there are very few valence electrons. Okay, so each atom in that crystal structure is going to lose those valence electrons. Okay, that's going to make these atoms, each atom, positively charged depending on how many electrons they're lost. So in this case for magnesium, we have a positive 2 charge here. So magnesium has a positive 2 charge. We lost 2 electrons, positive 2 charge. Okay, and those electrons are now in what we call the electron C. They are flowing throughout those magnesium atoms. Okay, and that is how metals get the properties that they have.